Gravei.
Thanks for the invitation to lecture. I just got in, so unfortunately I missed all the previous lectures, but I heard they were very nice. Hopefully you're all not too tired by now. I am pretty tired because I just took a 12-hour flight. Stop me at any time, ask questions. Please ask questions, otherwise I might fall asleep. So this is supposed to be interactive. The topic is gravitational scattering. Okay, so the plan, so we'll have 2 hours today and 2 hours tomorrow. So today the idea is to give you a little bit of the big picture of what we know about gravitational scattering, kind of both classical and quantum. So what is this about? So, okay, I'll discuss a little bit just GR as an EFT, in case some of you are not familiar with this. Then we'll discuss the phase diagram of gravitational scattering. So you'll see what I mean by this. So basically there's various regimes in which we can study gravitational scattering, and some of them we understand pretty well, some of them we don't understand at all. Then I'll also talk about the kind of various expansions that we can use to study gravity. So these are going to be things like this post-Minkowskian expansion, which I will explain, post-Newtonian expansion, so-called self-force, which is an expansion in mass ratios. And then, if I have time, if not tomorrow, I will talk about semi-classics. Okay. Okay, so what about tomorrow? So tomorrow will be about gravitational observables. Okay, so how we can use the gravitational scattering amplitudes to say things in particular about classical GR. And there will be kind of two perspectives on this. One is kind of an off-shell perspective, and there's an on-shell perspective. They're both based on amplitudes, but we'll see that one is trying to compute directly observable quantities using scattering amplitudes. The other one is going through some auxiliary objects like potentials and equations of motion and things like that. And then the other thing I want to discuss in some detail is the other related to this, the ways that we have to make predictions for these observables, which are the so-called in-in or in-out ways of computing things. So in-out is just the S matrix itself, but there's another way of computing things using the so-called in-informalism, so kind of real-time evolution, which is more familiar perhaps from solving equations of motion, but we can also do it using the S matrix. Okay, so that's the plan. Again, let me emphasize, ask questions. I'm happy to slow down and expand on anything. I don't have to cover all of the material. I'm not going to give many references, but you can come to me after and ask me. And also disclaimers, I'm going to use most of the time units where h bar and c equals 1, so natural units. Sometimes I will restore the h bar or c if I think it's useful. And then actually, in fact, for most of the talk, I will use what I call supernatural units where 2 and pi also equals 1. So I'm not going to be very careful with factors of 2 and pi because we are going to be mostly power counting and just trying to understand how different quantities enter at which orders and trying to understand kind of the scaling of various quantities. Okay? Sorry? Yeah, G I'm going to get, G is not going to be equal to 1. Yeah, I'm going to keep G around. Yeah, G Newton. All right. Any questions about the plan? Okay, so let's start it. let's get started with this first item, GR as an effective theory. So the basic idea is to try to understand when we compute some amplitude using general relativity, so the scattering of, say, gravitons, what we expect that we can predict and what we shouldn't expect that we can predict, okay? So this will be actually generic for any effective field theory, but the idea is to emphasize that GR is not special, okay? So we always say that, okay, GR is not renormalizable, but there's many effective field theories which are not renormalizable, but they're still predictive. So probably many of you are familiar with this, but perhaps some people are not. I just want to explain it so that we're all on the same ground. Okay, so we're going to start with just the usual Einstein-Hilbert Lagrangian. So we have something like this. But as an EFT, we're able to add any number of higher derivative corrections. So for instance, I can add, so at curvature squared order, let me just write it as R squared. But there's only one thing that I can write, because as in any EFT, we're always modding out by things that I can eliminate by the equations of motion, okay? Because these are things that can be removed by a Fourier definition. And in fact, I can adjust this, this term to be just kind of the four-dimensional Gauss-Bonnet term, which will be important in a little bit. But in principle, there's a whole tower here of higher derivative corrections, which are suppressed by some scale here, right? And this is just dictated by the derivative expansion, okay? So the curvature, this is roughly 2 derivatives of the gravitational field. So this is why we know that this thing here is something like m Planck to the d-2 dimensionally. And then this thing is going to have 4 derivatives, so this needs to be suppressed by some scale here. This is going to be suppressed by even a further scale, right? And then there's an important point, which is that whether this scale is of order m Planck or is much smaller than m Planck will tell me if the theory is kind of weakly coupled or strongly coupled, okay? So we'll see that we're going to compute some loops, and generically the loops coming from this are going to be suppressed by m Planck or inverse powers of m Planck. But these things might be much bigger if this scale is much lower than m Planck. Okay, so there's kind of a tree approximation that might be reliable. This is, for instance, what happens in string theory, where we have the string scale much below m Planck. But more generally, we could have just strongly coupled theory where lambda is of order m Planck, and then loops are important. And actually, for most of the time, we will consider this case. Okay, so if we are in this situation, what is the small parameter in this theory? So when we compute some quantity, so let's say that I want to compute some scattering amplitude, so I'm going to expand the metric on flat space. So there's going to be an infinite number of vertices. There's going to be some 3-point vertex, some 4-point vertex. So this could be kind of 2 derivatives, or if it comes with one of these higher dimension operators, it could be higher derivatives. So there's a whole tower here. Okay, and we are going to compute some scattering amplitude using these diagrams. But we're going to be doing perturbation theory. So, okay, what is the expansion parameter? What is the small parameter that we use? Yeah, it depends if you want your kinetic turn to be canonically normalized. It doesn't matter because the amplitude is field definition invariant. This is what I usually use, but yeah. But what is actually the small parameter? I'm going to wait till someone makes a guess. So, yes? G Newton is a dimensionful quantity, right? G Newton is 1 over m Planck. So small parameter needs to be something which doesn't have dimensions. So what is the, that's close enough, yeah? No, that would be 1, because G Newton sets m Planck. Yeah, yes? Okay, the mass over m Planck, or more generally the energy of the particles over m Planck, right? So it's going to be something like G E squared in the case of, say, 4 dimensions, right? So it's going to be G times some so this is equals 4. So it's going to be energy over m Planck. Okay, so that's the decimal parameter. So this theory is a derivative expansion. Okay, so when we compute things, we just need to count derivatives. Okay, and a lot of the things that we're going to do is going to so-called power counting. So we're going to write some diagrams. We're not going to compute them. We're just going to count how many derivatives or how many powers of certain parameter appear in these diagrams. So trying to understand the physics of it, which is what we always do in effective field theory. Okay, so let's do this. Let's get started. Let me write it down, because I didn't write it, but what we have is E over m Planck is smaller than 1, so this is called a derivative expansion. This is similar to pions. In pions, we also expand in like energy over f pi or over the cutoff of the EFT if it's much smaller than f pi. Okay, so let's power count. So let's think about 4-graviton amplitude. Let's just draw all the diagrams that we could draw, right? So there's going to be diagrams that look like this, some permutations, diagrams that look like this. Okay, so let's count this first. So counting derivatives is very easy. I have each vertex has 2 derivatives coming from Einstein-Hilbert, as I wrote there. So we're going to have here 2 derivatives. I'm going to have a factor of g. And I'm going to have an inverse propagator, like a propagator. So an inverse kinetic term, which is 1 over 2 derivatives. This vertex here also has 2 derivatives, right? So indeed, this goes like g is squared. Okay, so this is small, as we said. Okay, let's keep going. So let's add, for instance, this diagram. There can be more complicated things. Okay, so a trick is that when you're looking at some order, because every vertex and every propagator has the same number of derivatives, you can cancel them. So if you pinch some propagator, you can do it for free. So to power count, you can always look at the simplest diagram. So let's look at this diagram here, which is the simplest diagram. Okay, so how does this go? So this is, let's do it in 4 dimensions for simplicity. There's a D4L. There's 2 vertices, right? So I'm going to have an L to the 4th. In the numerator, there's 2 propagators, so there's going to be L to the 4th. And there's going to be 2 factors of g because I have 2 propagators or 2 vertices, right? So this is going to be like g squared e to the 4th. So indeed, this is smaller than this. However, in practice, yes?
I would assume that I know how to build a series in field theory. So, but when you're saying about the diagram, what we treat as a field, I would also assume that it has some propagator based on some quadratic form in the Lagrangian. And what is this in this case? So this diagram represents.
Sorry, yeah. These are all gravitons. So here I just have gravitons. I'm scattering gravitons. So you would have a graviton propagator, which in terms of this Lagrangian is that when you write this expansion like this, right? Okay, so I'm not going to go over kind of perturbative gravity in detail because I just want to count derivatives. I don't want to explain how to quantize gravity. That would be a topic for a different course. But the idea is that if I plug this into the Einstein-Hilbert action, there's going to be a term that is quadratic in this fluctuation with two derivatives. And if I choose an appropriate gauge, then that will give me a kinetic term for this fluctuation, which is the graviton, and then I can just compute diagrams, just like I do in field theory. So the same way that for electromagnetism, you're doing the field theory of a massless spin 1 particle, from this EFT perspective, GR is just the theory of a massless spin 2 particle. Yeah, it's a fluctuation around flat space. Yeah. Okay, good. That was a nice question. More questions? Yes.
But if we include the higher derivative correction, it is not non-countable for the it can be changed.
Okay, so this is a big difference between treating these theories. So that's also a very good question. So depending on which community you're from, then you can take this Lagrangian, this action literally, where you think that these corrections can be large, and then you would have to include them when you compute things like, you compute how many modes you have and stuff like that. But in EFT, we always treat them as a perturbation, okay? So this never affects, like this R squared, R2 cubed, et cetera, it never affects the kinetic term. It's just a small perturbation, so it gives us vertices, but it doesn't give us kind of new modes or corrections to the propagator. So yeah, for instance, if you take this literally, that would be like a 4 derivative term. So naively, you could have a ghost or something like that. So you would need to be careful. But if it's a small perturbation, then that won't be there. And in field theory, it's the same, by the way. So in field theory, not only in gravity, but if you integrate out some massive particle, you generically will generate these higher derivative terms, and you know that there is no ghost in the spectrum, right? It's just some low energy expansion. Yeah. Okay. One more question. Okay, so what's the catch with this power counting result that I wrote here? So the catch is that typically when we have something like this, okay, you might have this counting, right? There could be some like power divergence that we can always tune to 0, et cetera, but generically this could appear with a logarithmic divergence, okay? So this thing generically won't appear like this, but it will appear with a log of E over lambda, where lambda is some UV cutoff, which or some renormalization scale, depending on which kin you're using. Okay, or said another way, this could have like a g squared e to the 4th over epsilon pole if you're computing using Limbrag. Okay, so this is telling me that actually this perturbation theory, there's something missing, and indeed here I could add this R squared, this 4 derivative term, which comes from the R squared operator, which will absorb this UV divergence. Okay, so when I add this, whatever UV divergence that appeared here at this order in the derivative expansion, right? So this thing will come with some coefficient. Let me call it CR squared. And then I can choose it to be this kind of 1 over epsilon or log lambda, which will absorb this UV divergence. But then there's also some finite part that it's not determined, okay? So it's just whatever the value of this coefficient was, apart from it absorbing the UV divergence. Right. And this is actually where the difficulty lies, is the fact that a priori we don't know what the value of this thing is. So for instance, if you have some more microscopic description, say string theory or your favorite UV, then that might come with a particular value for this coefficient here. You might not even have a divergence if the theory in the UV is well defined. But a priori, there's nothing that fixes this. And if I want to determine the amplitude to this accuracy, so if I want to determine the amplitude to G E squared, then this is completely fine. This is just fixed by Einstein-Hilbert. But if I want to know the amplitude to accuracy G squared e to the 4th, then I need to know the value of this counter term. Okay? This is the same in every effective field theory. Okay? So effective field theories give you predictions at fixed accuracy. And if you want more accuracy, you need more and more information, which are the values of all of these Wilson coefficients. Okay? Okay, is that clear to everyone?
The point
배기원 move lambda to here.
So maybe this is confusing. So maybe I should write mu squared. So this is a randomization scale if I'm using dimreg. But the idea is that generically this coupling is going to run. Okay, so it's going to have some logarithmic dependence on some scale, which I can choose using some scheme, and that also tells me at which scale I'm measuring this coefficient. Okay, so this also depends on mu generically. Okay. So two very simple comments. The first one is that, so one thing that is special about non-normalizable theories like GR is that the running, this is it. It's not like if you have a marginal coupling like in QCD, we're used to computing like 2-loop beta function, the 3-loop beta function, et cetera, right? But here, the dimensionless parameter is something that has a dimensionful scale, right? Which means that you can have mixing between different operators, but the running of this thing, there's no higher correction. So as far as G Newton goes, this is it. There's no kind of log squares that one needs to resum that will appear further down in the perturbative expansion. And then the other important thing is that the coefficient of this log, this is a prediction from GR. Okay, so the finite part under the log, which is this coefficient here, that we cannot predict, but the coefficient of the log is actually predictable. Okay, so this is because, well, first of all, it's a part of it's associated to an actual physical scale in the process, which here is the energy, right? And that means that we can take a discontinuity and will be fixed in terms of lower order things, which we know were unambiguous. So for instance, there was this true level amplitude here, which was unambiguous, right? So the imaginary part of this one loop amplitude will be given by some unitarity cut. I think Sebastian was telling you about these things earlier. And that's completely predictable, okay? And this is a more general point, which is that these finite parts is the thing that we cannot tell ahead of time, but non-analytic pieces of the amplitude typically are under control. And that will be important once we try to understand how kind of classical GR arises from this whole story. Okay, and also let me make an aside in case someone is confused. In D equals 4, there's an accident, which is that R squared operator, I told you I can always choose that to be the Gauss-Bonnet operator. And in D equals 4, this Gauss-Bonnet operator, which people sometimes call E4, which is basically Riemann squared plus et cetera, this is a total derivative. Okay? So this is the derivative of some like Chern-Simons form in 4 dimensions, which means that actually if you go ahead and do this computation, you won't find a divergence by accident, because the coefficient of the divergence, it just happens to be 0 in 4 dimensions or not contribute to a scattering amplitude. Okay, so the first divergence in 4-dimensional GR actually is associated to this R³ operator, and that's a divergence at 2 loops. Okay, so let me give you a little exercise. R count the 2-loop amplitude and see that this will go basically like this R³ operator. Okay, so it should be very similar to what we just did. Okay, any questions about this? So the lessons are, first, we can compute order by order in this derivative expansion, but we will need more and more information, but the logs are fine. Okay, and this was going to be a theme in many of the things that we're going to look at. This is this Gauss-Bonnet term. So it's just some particular combination of Riemann squared, Ricci squared, and Ricci scalar squared, which I forget the particular coefficients. But if you look it up, I can also look it up later if you want. But it's just the thing that would appear here, kind of at the subleading order in the derivative expansion. Okay, so But there's something funny here. There's a couple funny things in what I said. So this is all fine. But then let's think about classical processes, okay? So in order to be able to do perturbation theory here, I needed G E squared to be much smaller than 1, okay? Or this is the same as E over M Planck squared. Okay, but what is M Planck? In kilograms. Something like 2 to the 10 to the minus 8 kilograms. Okay? And what is E of a human? So if a human, just its rest mass, let's say it's like a pretty hefty human, so it's something like 100 kilograms. Right? So this means that E of a human divided by M Planck, this is like 10 to the 10. Okay? So why does GR work? Also, there's something else funny, which is that if we just take two particles in the absence of any other forces, right, and we just let them gravitationally interact. So let's think these are like really point particles, right? So they don't have any structure. Nothing's going to stop them from getting closer and closer and closer, and eventually coming inside the effective Schwarzschild radius, which is given by the sum over their masses. So if these particles don't have other forces that keep them apart, like nuclear forces or anything like that, they're going to form a black hole. Okay, and so this is a very low energy process. These particles don't need to go very fast. They just need to get close enough. So at short distances, we know that something else happens, which naively here we cannot see. Okay. Okay, so what this means is that actually when we do classical gravity or classical gravitational scattering, this G squared parameter is not the small parameter. In fact, this is a large parameter, as we just saw. Okay? Take the sun. The sun is like 10 to the 30 kilograms. Okay? So when we compute the orbit of the Earth around the sun, then this is now like something like 40 orders of magnitude. Okay? So there has to be some other small parameter that we can use that tells us that it's okay to do classical GR. But it's not the one that we use when we treat GR as an EFT and we just compute derivatives. Okay, so let's try to see if someone can guess what is the other small parameter. H bar, okay, H bar we set to 1, but right, okay, so let's think about which quantities have the same dimensions as H bar in physics. So what is quantized in units of H bar? Sorry? Action, that's a good guess. In fact, that will play a role later, but we'll see that actually our actions are large because the action roughly scales like this. Okay, there's a simpler thing. Yes, exactly. Okay, so let's see what the small parameter. So if we want to do classical GR, we're always talking about macroscopic objects which have angular momentum. What do we mean by that? What we mean is that the Compton wavelength of the object is going to be divided by the separation between whatever objects that we have. This thing needs to be very small. Okay? Right, so we have some objects which are, maybe they're quantum, but if they're very far away from each other, we're avoiding all of these short distance issues, right? So here we said that if we have two objects that come very close together, they're going to form a black hole. here we have these ambiguities in the derivative expansion, but these ambiguities are always contact terms, okay? Because there are UV ambiguities. They're always something at short distance. So in position space, this is just something which is localized in space and time. Okay, so this is something that you will only see if really things come on top of each other. Okay, so if we keep things apart, we can still make good predictions with GR, right? And why is this related to angular momentum, right? So the Compton wavelength, or let's take like the de Broglie wavelength, maybe it's a bit easier to see. So what is this? This is going to be like h bar over p, and then we have r, but pr is the angular momentum. And then we are saying that this is much more than 1, which means that we are looking at things that have large angular momentum. Okay, so next I want to explain, we're going to think of amplitudes both in momentum space and in position space, or in impact parameter space, which is related to this angular momentum. And we're going to see kind of what is the scaling that will allow us to do some sort of perturbation theory. Yes? Not necessarily. The idea is that there's some like characteristic wavelength that has to do with the energy of the object, and I want the separation to be bigger than that. Yeah. Yeah. Any other questions? You can also choose the Compton wavelength, but then for the translation, there will be an extra factor of velocity that you need to tell me if it's large or small. Yeah. What time is it? Ah. Okay. So let's see. So let's think about this 4-point amplitude, first in momentum space. So just to set up the stage. So I'm going to use the usual Mandelstam variables. I'm going to have P1, P2, P3, P4. And the S is basically the center mass energy squared. T will sometimes write as minus Q squared, which you can also think as E squared times squared of the scattering angle. And the amplitude will be a function of S and T. Okay, so maybe it's unclear right now how the scaling will pan out. So let's think about it in position space. So this is so the idea here is that we have these wave packets or these particles that have this characteristic size, which could be like the Compton or the de Broglie wavelength, and then there's going to scatter with some fixed impact parameter B, which is much larger than this. And what do I mean by the amplitude in position space? I'm going to Fourier transform T, so Q, as follows. So I'm going to have dq. I want to maintain, so since P1 plus P4 is Q squared, that means that Q is the difference between P1 and P4. So I'm using kind of an all outgoing notation, which means that P4 is minus P1 plus Q, essentially. But I want to maintain the on-shell condition of P4, right? So the on-shell condition of P4 would be P4 squared minus m squared, but this is the same as p1 plus q squared minus m1 squared, and now we'll have the same for p3, p2 minus q squared minus m2 squared. And then I have just e to the I q dot b, and then the amplitude as a function of s, and t, which is minus q squared. And we'll do some of these calculations later. But the idea is that if we want b to be very large, for this integral to give me something reasonable, then actually that will mean that q is very small. Okay. And we said that s generically is going to be large, because we are looking at some kind of macroscopic scattering. So that means that if s is large and t is small, that means that we have to look at very small angles. Okay. So here, this classical limit is just kind of q squared much smaller than s, or small angles. It's not exactly like the soft limit. It's a soft limit, and I'll call this soft in a second. But typically, when we think about soft limit of an amplitude, we're thinking about take the momentum of one particle, right, and make it small relative to the momentum of the others. So if you wish, this is the soft limit of whatever particles are exchanged between these two, right? So for instance, if I have this diagram that we drew earlier, the momentum of this will be q, right? And then when p1 is very close to p4, so when the scattering angle is very small, that means that this q actually will be very small. Okay, so there's something going soft, but it's not an external particle. Okay. Any more questions?
We're imagining a small momentum transfer, and we're labeling 4 as the output of 1, 3 as the output of 2.
That's right. So we are writing P4 as minus P1 plus Q, and P3 as minus P2 minus Q. All right. So let's revisit the relevant scales with this in mind in the scattering problem, gravitational scattering. So we said that we have something like the Compton or the de Broglie wavelength, right? So this is going to be something like h bar over m, or h bar over the momentum of some particle, which are the particles that I'm scattering. And I want this to be small, so I'm like something very heavy or something very energetic. Then the other scale, so let me call this the effective Schwarzschild radius of a particle as a function of the energy. So this is just g times E. Okay, so now it's in 4 dimensions, otherwise this is the Schwarzschild radius to some power that depends on the dimension. And then the last scale is just B, or R, which we said is kind of 1 over Q, because I want the exponent there to be order 1. Right? So notice that the EFT expansion, so let me write here also something like h bar over E. The EFT expansion, which g e squared small, actually is the limit where this thing is much smaller than lambda. Okay? Because if I take the ratio of RS and this, then that gives me g e squared or GEM or EP, right? So this is definitely not classical. We are saying that there's an object whose Schwarzschild radius effectively is smaller than its Compton wavelength. just its characteristic quantum size. Okay. So that's not the limit that we're going to take. Actually, the limit that we're going to take classically is this hierarchy here. So we're going to say that the largest scale is the separation between the particles. For convenience, we'll also take this to be smaller so that we have another expansion parameter, which is basically short shear radius divided by the separation, right? So we want RSE over R to be smaller than 1. So we can actually do perturbation theory in G Newton. Otherwise, this would just be kind of very strongly coupled. Okay, in GR, we can also solve this sometimes. We can put Einstein's equation in a computer. So we'll mention that in a second. But we're going to do some scattering amplitudes computation. So we're going to do perturbation theory. So this will be our perturbative parameter. So notice that this is just a weak field expansion. This is also what people call this post-Minkowskian. And written in terms of the parameter of the scattering, this will be something like GEQ or GMQ if you had something very heavy where most of the energy comes from the mass. Okay, so this is actually the small parameter to do perturbation theory in weak fields. It's not G times the energy. It's G times the energy divided by the separation. Okay, and there's another small parameter. Which is coming from the other hierarchy here. Well, there's actually two of them, but I'm going to choose the largest or the smallest one, which is going to be kind of lambda over R or lambda over B, which this is going to go like Q over P or Q over M or Q over the energy. So this is what we were saying earlier, that Q is going to be very small relative to the other scales in the problem. It's the same thing that I said here. Okay, so when we do classical perturbations in the weak field limit, we're actually doing some double expansion. There's this expansion here. Powers of this expansion will control classical versus quantum corrections. Okay, and powers of that parameter, GMQ, will just compute kind of classical, kind of weak field corrections. Okay, so in GR, we can do just, in the classical realm, we can do just perturbation theory in the weak field. But we could also include quantum corrections, which will be suppressed by Q over M. Okay. So there's weak field, and then Q over M. This is quantum. Okay, in D dimensions, one has to be a bit more careful. Let me just comment here, because GE is not R Schwarzschild, is actually R Schwarzschild to some power. So in D dimensions, the expansion parameter will be something like GE over R to the D minus 3, which is kind of RS over R to the D minus 3. Okay, so the Newtonian potential in the dimensions goes like 1 over R to the D minus 3, not 1 over R. Okay, so I'm going to wait to see if there are any questions, because the next thing that we're going to do is we're going to draw a phase diagram of gravitational scattering, both as a function of the energy and as a function of this impact parameter, and see where we can actually predict things and where we cannot predict things. But before I do that, let me just pause for questions.
Say that there are these two possible
parameters we can consider.
Yeah.
So this basically DEQ and Q over M. I think it's written in there graviton versus plasma.
Quantum. So this parameter controls quantum corrections. So if I include more powers of this, I'm going more and more quantum, because this is the same as what I wrote there. This is essentially the de Broglie wavelength divided by R. This is just nonlinearities in classical gravity. Yeah. So there's higher orders in perturbation theory in classical gravity, which are just kind of corrections in the strength of the field, which we can compute, right? So I don't need to quantize anything. I could just compute in GR perturbatively in the weak field, and then I would just be computing these corrections. Yeah, or corrections to like the scattering angle. We'll talk tomorrow about observables if we have time. So yeah, you can compute like the deflection angle of light, kind of in the weak field of the sun, like this famous first test of GR, and there's going to be corrections to that, which go with like higher powers of R, S over R. Yeah. This is just that this thing that I wrote here, it's in 4 dimensions because the G times E in general dimension is some higher power of the short sheet radius. It's just dimensional analysis, but because in a second I will write this phase diagram in the dimensions, I wanted to just remark. Yeah. Okay, more questions. You guys are doing a great job of keeping me awake, so. Well, so far here I just call this like this effective short sheet radius, which depends on the energy of the system, right? But indeed, when we talk about classical scattering in a bit, then this will be the mass, for instance, and this will be literally the short sheet radius. And the idea is that, say you have a binary black hole, while they're far away from each other, I can always expand because they're in the weak field of the other guy, and then I can do perturbative calculations. When they come very close, I can't, then I need to put Einstein's equation on a computer. Yeah. Okay, more questions? Yeah.
What parameter is your good parameter and what parameter is out of this parameter? Like M is out of this parameter.
Sorry, can you repeat that?
What parameter is Gravitation's parameter and what parameter is out of this parameter?
So the question is, which one is like genuinely gravitational? This is the actual gravitational expansion. This I could have said for any system. So for instance, you could also have some like classical electromagnetic system, right? And you can consider this limit here, right? So this is just considering classical versus quantum. So this is really telling me that we're doing something with gravity. Yeah. But this is a more general statement, that this encode kind of quantum corrections. Okay. So let's draw the phase diagram. Okay, so before I draw it, just a couple comments. So this is actually some qualitative phase diagram that people develop over the years. And by over the years, it's mostly the late 80s and the early 90s by Amati, Ciappellone, and Veneziano, right? And actually our understanding is kind of frozen then. Now we know how to compute more accurately in perturbation theory, and we've been very effective at doing this in the last few years. But as far as this phase diagram goes, we haven't made a ton of progress. Okay, so I think it's good to keep it in mind and think if you have any new ideas, especially young people, to attack how to understand transitions between the different phases in here. Okay, so phase diagram is going to be. Okay, the x-axis is going to be log of the energy in some units, and the y-axis is going to be log of the impact parameter. Okay, so before I draw any lines here, which are the regions that people think are going to be problematic, when we don't really know how to make predictions in general for a scattering process? Large E? Sorry? That's right. Okay, so around here, things are going to get complicated. And around here, things are going to get complicated, right? Short distances or high energies is where UV enters, right? So indeed, around here, there's a big question mark, right? For small enough B's, then we don't really know what's going on, right? Okay, what is the difficulty here? So perhaps the simplest line to understand is there's a line here of some sort of phase transition, right? Which tells me that really I have like very strongly coupled gravity, right? And for high enough energies, it's going to be quantum. So this region here, it's called the collapse region, right? And this is when the relation between log of the energy and the impact parameter, this goes like 1 over d minus 3. Let me check that this is correct. Yes. Okay. Now, this is very easy to understand. Where does this 1 over d minus 3 come from? It's exactly this d minus 3 here, right? So this is precisely when the impact parameter is of the size of the effective Schwarzschild radius, right? And I told you that GE goes like RS to the d minus 3, right? So if I say that this is order 1, that means that the radius of the impact parameter goes like 1 over d minus 3 as a function of the energy. Okay, so this is kind of B is like e to the 1 over d minus 3, or kind of RSE is of order B, right? So this is really kind of the strong coupling region. We kind of know what happens. We know that when we scatter things at those energies, they're going to form a black hole, but we don't have any detailed understanding of that process quantum mechanically. And you could just compute this in classical GR. There's a question whether this is under control or not. Yes? Well, this is where something qualitatively different happens. I mean, let me put quotation marks here. And for instance, here, the thing that is going to change between some of these, one of the things that's going to change is how large the S matrix for this 4-particle scattering is. So for instance, here we know that the probability of scattering 2 particles at these energies, and then 2 particles to go out, is essentially 0, because with almost certainty, we're going to form a black hole, right? So this is a region where the S matrix is going to be of order 0. Yeah, exactly. Yeah. Okay, so what is the region now that we have completely under control? What is the simplest region of all? Yeah, so around here, right? Like very large B's, we were just discussing that this is fine, right? And then if B is very, very large compared to E, right? Then it could be that even this tree-level approximation is valid. Okay, so so here there's this what's called Born regime, right? So this is kind of okay. So let's think about this in a second. We want to draw some line here to see until when this Born regime is valid. So what is the characteristic of this? The characteristic is that the tree-level amplitude is a very good approximation to the amplitude, to the full amplitude, which also means that S is basically 1. Okay, so the scattering is almost elastic. We know that these things are just going to scatter elastically off each other, and we can even compute with which probability, which is very small. Okay, so let's do a small calculation of this thing in impact parameter space, right? So first of all, let's compute this amplitude. Let's take 2 scalars for simplicity instead of gravitons, right? And I'm going to be lazy. I'm not going to compute Feynman diagrams, but I'm just going to tell you the answer. You can check that it's correct by showing that it factorizes correctly if you put this, this pole here on shell. Okay, so this amplitude is something very simple. It's simply 8 pi g p1 dot p2 squared over q squared. Okay, so these are distinguishable particles which are massless, right? So basically this goes like g times the center of mass energy to the fourth divided by q squared. Okay, and now I'm going to do the Fourier transform, which I unfortunately erased. So this is kind of, so this is the same as t. So this is a of s e minus q squared. So okay, center mass energy squared is just s. Okay, so now I'm going to write a of sb. So I want to do the Fourier transform, but because q is much smaller than the other scales, I can expand away all the q's inside of these delta functions. So this is going to simplify significantly. So this is just going to give me the q e to the I q dot b delta 2p1 dot q delta 2 p2 dot q. In principle, there could be a q squared in here, but I told you it's very small. Right, and then I have this gs squared over q squared. Okay, so this is essentially a Fourier transform in the transverse direction to these two incoming momenta. Okay, so this is like a d minus 2-dimensional Fourier transform. There is a Jacobian, which is just the product of p1, p2, right? So actually, I'm just going to write that Jacobian, which is 1 over s. And then by dimension analysis, you know that the d minus 2 Fourier transform of 1 over q squared is going to go like 1 over d to the d minus 4. Okay, so this is going to go like gs b to the d minus 4. Okay, so d minus 2 comes from the measure. Okay, you can also think that each one of these guys goes like 1 over q, and this goes like q squared. And then there's the Jacobian. Okay, and remember, s goes like the energy squared. So this is like g e squared b d minus 1. Okay, so this Born regime, so this will be a good approximation to the amplitude as long as this is a small quantity. But at some point it might become large. So we need to be careful because, okay, we said that g squared is large, but we're taking b to be very, very, very large so that this is still small. But as we change b, then we can transition into some other region, or as we increase the energy, right? So what is the boundary there? The boundary is going to be when this is order 1. Okay, so when I cannot trust this because there might be corrections that go like powers of this. Okay, so the boundary here, the slope is 2 over d minus 4, which is just when this thing is order 1. So this is when kind of a squared d minus 4 is order 1. Okay, and what happens next? Well, what happens next is that in this process is just saying that these particles come, they scatter once through the Newtonian potential, and they don't see each other ever again. Okay? But actually, that's not what happens in most gravitational processes. There can be some complicated interaction. They can interact for a long time. Okay, so there's going to be some region in here. So let me draw another boundary here, which is going to be dominated by semi-classics. So this region here. So this is going to, what does this mean? It means that the amplitude actually, this tree-level approximation won't be good because this will be large. But what we expect is that the amplitude actually will go like e to the I, some classical action over h bar. Okay, so we expect some sort of exponentiation. And we'll see later that that happens when we actually sum a bunch of diagrams. So there's diagrams that look like ladders or things like that, that they all contribute as powers of the same quantity, which is basically this quantity that we need to resum. So this is still something classical, But the amplitude now is not the right thing to look at, is the logarithm of the amplitude, which is just the usual classical action. Okay? But notice that because this is still e to the I times something, in here, this is still order 1. Okay, so here is just our description changes. This is not enough, but we still know what to do. This is just classical dynamics, which is what most of the rest of this course is going to be about. Okay, and there's a last boundary here, which is perhaps the most interesting, at least since 2015. So what is the other thing? So when does the amplitude stop being order 1, but will start decreasing at least a little bit? So this is the amplitude for just scattering two things gravitationally and the same two things coming out and nothing else. Okay, so what is the process that we expect that will kick in if we increase the energy a little bit more, or if we decrease the impact parameter so things become even closer? Exactly. So radiation, right? You said, well, maybe that's not what you meant by emergence of a new particle, but what can happen is that so basically gravitational waves. Okay, so this means that the amplitude now will be slightly less than 1. Okay, so now there's other processes which are important, which are things like, for instance, this. Okay, and now I'm going to do a little calculation to show you what the slope is here, which is actually a weird number, but you'll see that it makes sense. So the slope is 4 divided by 3D minus 10 in the dimensions. Okay. Okay, so why is this true? So what is a relevant thing here? Let me go here. Yes. Can you repeat it? Yes, yes. I mean, there's let me put. Yeah, the idea is that this becomes now a significant process. Okay, so now that the amplitude at these energies or at these impact parameters, there's a significant contribution from like emission of gravitational waves. And before, I mean, it's always there, but it's so small that it's negligible. But when you hit this boundary here, then it's not negligible anymore.
States, or are we also thinking of?
This is all scattering. This is all scattering. Yeah. Yeah, it depends what you scatter. You will form bound states or not, and depends how much radiation is radiated away. If they're massless or massive, yeah. Yes.
What is it that tells me that I can't do all the calculations for you? Like I can't have a formula.
Well, you mean this thing here?
Yeah.
This is not that you cannot do it. Is that these won't be straight lines. Because whenever you have some parameter to the 0, what this means typically is that it's a logarithm, right? So in 4D, what happens is that this boundary is not linear. It's just when e squared log b is order 1, right? So this is some exponential or something. So it's more complicated. So that's why I wanted to do it in d dimensions, because these are all straight lines with different slope. But in 4D, there's still a boundary. But now it's not straight. Yeah.
What happens to the line for gravitational waves?
In 3D? In 3D, there are no gravitational waves because there's no dynamical gravitons. So if you count the number of felicities, it's yeah, 0. Or degrees of freedom, yeah. Okay, so let's try to understand at least roughly this power. And this will be a warm-up exercise for something that we will do later much more, which is kind of power counting various diagrams and trying to understand the various contributions from them, right? So what is the cross-section for this production of like now some extra graviton in the final state, right? So this will be something like this thing squared, right? But by the optical theorem, this is just the imaginary part of some 4-point amplitude at some order, right? So if this is the tree-level amplitude, right, this will just be the imaginary part of well, something like this. So it would be some unitarity cut. Okay, so let's look at the simplest diagram that looks like that. Yes. How do I know that is unitary? Well, perturbatively, it's definitely unitary, which is everything I need to use here. There's subtle questions like how is unitarity restored when you go to high energies? For instance, here I was mentioning that this exponentiation helps. So you might seem that the amplitude is growing very fast, but then if you actually exponentiate, it's just a rapidly varying phase. So generically, it's a subtle question, but definitely in perturbation theory, we know that it's unitary because we can see that there is no ghost, which is more or less everything unique. But actually, I don't really need this. I just need to. I'm going to power count some two-loop diagram. That's why I mentioned this, because I just want to understand what is the size of this thing, and I'm going to look at some two-loop diagram to try to estimate its size and see when this thing becomes large. Okay. So this is a very simple calculation. So let's do it. So let's look at the simplest diagram that looks like this. It's going to look something like this. So it's a two-loop diagram. Okay. Okay. This thing is on shell, but it doesn't matter much because I'm just going to count derivatives as before. Okay. But now we have two types of momenta here. We have the momenta of the external particles, which are large, and then the momenta of these gravitons, which are small. Okay. We were saying that Q is much smaller than S, or Q is much smaller than the momenta of the particles, right? So, okay, so let's count. So, well, first of all, this will have, there's two loops here, right? So this would be like d to the 2d. Okay, there will be two loop momenta, but let me just write it like this. There's 1, 2, 3, 4, 5 graviton propagators. So this is an L squared to the 5. There's two vertices, which are just gravitons. Let me put an L squared squared. Okay. And now comes the tricky part. So there's these vertices here. So at the leading order, because these vertices here are dominated by the external particles, the momenta of the external particles, I can just say that these go like the energy of these particles or the momenta of these particles. Okay, so I'm going to have 1, 2, 3, 4. Each vertex, because this is a gravitational theory, it's two derivatives. Okay, so this is going to look something like P1 to the 4th, P2 to the 4th, roughly. And then there's also these propagators here. Okay, so these propagators here, what do they look like? So if this is L, right, this is going to look like P1 plus L squared minus M1 squared, if this was particle 1. But L is very small. So P1 squared equals M squared. So at leading order, this is 1 over P1 dot L, or 2P1 dot L, when P is much larger than L. Okay, so this is plus some correction, which will be powers of L squared over so this is suppressed by Q over M. So remember, we said that one of the expansion parameters is Q over M. So if we think that all of the gravitons are order of the momentum transfer, we'll make this more precise later, but this will give me something like this. So here I'm going to have a P1 dot L, P2 dot L. Okay, so what does this mean? So this diagram is going to go roughly like Q1 cubed, E2 cubed, and then all of the powers of L, so they're of order of Q because these are gravitons which are exchanged. So I just need to count them. So what is the count? The count is going to be Q to the 2d minus 4. Okay, so you can count here. So you have 6 powers of L squared minus 2. All right, we're almost done. Now we're going to do the Fourier transform to impact parameter space to see when this thing is large. So if I do the Fourier transform, remember there was a Jacobian that went like 1 over s. So this thing is going to be, so we have s to the cubed divided by the Jacobian. And then we had q to the 2d minus 4. So this is going to give me a 1 over 2d minus 4. And then from the measure of the Fourier transform, we're going to have an extra factor of d minus 2. So this goes like s squared over b to the 3d minus 10, which is the same as e to the 4th b 3d minus 10. And then if this is order 1, this means that b goes like. Okay, so this becomes large precisely when we have this relative scaling between the impact parameter and the energy. Okay, and what will happen there is that this imaginary part, so even if you have a classical process and things exponentiate, there will be an imaginary part here that will give you some exponential damping that will go precisely like powers of this thing. So the amplitude will become less than 1. Okay, any questions about this? So in summary, before the questions, I mean, we kind of know what happens here, but we cannot compute. This is trivial. This is interesting. This is where classical dynamics is. This is even more interesting. This is where gravitational radiation is. So for the rest of the lectures, we'll focusing mostly in this regime here, which is the one that we care about since we observed gravitational waves about 10 years ago. But are there any questions?
Okay, we have already enough questions, so we should take a break. Okay, thank you for thank you, Julio, for interesting lecture, and we'll resume at 55.
Okay.